Yes, this is a code violation. National Electrical Code Section 300.3c states conductors of different systems accepting the use of multi-conductor cables shall not be permitted in the same raceway, cable tray, armor, or enclosure without a suitable barrier between them. Normally an 18 American wire gauge wire would be used for 24 volts and a 6 American wire gauge wire would be used for 220 volts, so you have a mixture of systems in the same raceway. A suitable barrier, such as a ground bar, would be required to separate the two systems. Let's delve deeper into the specifics of this code violation and explore the rationale behind it. Mixing conductors of different systems within the same raceway, cable tray, or enclosure without proper separation presents several potential hazards. Firstly, the insulation on the lower voltage conductors, such as the 18 American wire gauge control wiring, is typically designed for lower voltage levels. When these conductors are run alongside higher voltage conductors, such as the 6 American wire gauge conductors carrying 220 volts, there is a risk of insulation breakdown. The higher voltage can stress the insulation of the lower voltage conductors, potentially leading to arcing, short circuits, and even electrical fires. Secondly, the presence of both high and low voltage conductors in close proximity can create electromagnetic interference. The higher voltage conductors can induce currents in the lower voltage control wiring, which can disrupt the operation of sensitive electronic equipment connected to the control circuits. This interference can cause malfunctions, errors, and unreliable performance in the control system. Thirdly, from a safety perspective, mixing high and low voltage conductors in the same raceway can create confusion and increase the risk of accidental contact with live parts during maintenance or troubleshooting. Electricians working on the system may not be aware of the presence of both voltage levels, which can lead to serious electrical shock hazards. The National Electrical Code, or NEC, recognizes these potential hazards and addresses them in Section 300.3c. This section specifically prohibits the mixing of conductors of different systems in the same raceway, cable tray, armor, or enclosure unless a suitable barrier is provided to separate them. The term different systems refers to circuits operating at different voltage levels or serving different purposes. In the scenario described, the 18 American wire gauge control wiring typically used for low voltage control circuits, and the 6 American wire gauge conductors carrying 220 volts represent different systems. The purpose of the suitable barrier is to provide physical separation between the high and low voltage conductors, preventing them from coming into direct contact. This barrier also helps to reduce the risk of insulation breakdown, electromagnetic interference, and accidental contact with live parts. One common type of suitable barrier is a ground bar. A ground bar is a metal bar that is connected to the grounding system of the electrical system. It provides a low impedance path for fault currents to flow back to the source, helping to quickly trip circuit breakers or fuses in the event of a fault. When used as a barrier between high and low voltage conductors, the ground bar is typically installed within the raceway or enclosure, physically separating the two systems. The ground bar is securely mounted and properly grounded to ensure its effectiveness. In addition to a ground bar, other types of suitable barriers can also be used, such as insulated dividers or separate compartments within the raceway or enclosure. The specific type of barrier required will depend on the size and configuration of the raceway or enclosure, as well as the voltage levels and current carrying capacity of the conductors. It is important to note that the exception to the rule in NEC Section 300.3c allows for the use of multi-conductor cables. Multi-conductor cables are cables that contain multiple conductors within a single jacket. These cables are designed and manufactured to meet specific safety standards, and the conductors within the cable are typically insulated and separated from each other. When using multi-conductor cables, it is generally permissible to run conductors of different systems within the same cable, as long as the cable is properly rated for the highest voltage present in the cable. However, it is always important to consult the cable manufacturer's specifications and the relevant sections of the NEC to ensure that the cable is suitable for the application. In the scenario described, the use of separate, single conductor wires for the 18 American wire gauge control wiring and the 6 American wire gauge conductors carrying 220 volts would not meet the requirements of NEC section 300.3c unless a suitable barrier is provided. To comply with the code, one option would be to install a ground bar or other suitable barrier within the raceway to physically separate the two systems. Another option would be to use a multi-conductor cable that is specifically rated for the voltage and current requirements of both the control wiring and the 220-volt circuit. When selecting a multi-conductor cable, it is important to consider the ampacity of the conductors, the insulation voltage rating, and the environmental conditions in which the cable will be installed. It is also important to ensure that the cable is properly supported and protected from physical damage. In summary, running control wiring with a 220-volt circuit in the same raceway without a suitable barrier is a code violation under NEC section 300.3c. To comply with the code, a ground bar or other suitable barrier must be installed to physically separate the two systems, or a multi-conductor cable that is specifically rated for the voltage and current requirements of both circuits must be used. Failure to comply with this code requirement can create serious safety hazards, including insulation breakdown, electromagnetic interference, and electrical shock. Always consult the NEC and other applicable codes and standards when designing and installing electrical systems, and seek the advice of a qualified electrician if you have any questions or concerns. Now let's consider some additional factors related to this code violation and how it might impact the specific installation described. The initial question mentions that the wiring is for a condenser on the roof. This indicates that the installation is likely subject to additional requirements related to outdoor and rooftop installations. Firstly, the National Electrical Code has specific requirements for wiring methods and materials used in wet locations. Since the condenser is located on the roof, it is likely exposed to rain, snow, and other forms of moisture. Therefore, the wiring and raceway must be suitable for wet locations. This typically means using weatherproof conduit, fittings, and boxes, as well as conductors that are rated for wet locations. Secondly, the NEC also has requirements for the support and protection of wiring on rooftops. The wiring must be securely supported to prevent it from sagging or coming into contact with the roof surface. It must also be protected from physical damage, such as from foot traffic or falling objects. Thirdly, the NEC has requirements for the grounding of electrical equipment installed on rooftops. The condenser must be properly grounded to ensure that any fault currents will flow back to the source and trip the circuit breaker or fuse. This typically involves connecting a grounding conductor from the condenser to the building's grounding electrode system. In addition to these specific requirements for rooftop installations, there are also general requirements for the installation of electrical wiring in accordance with the NEC. These requirements cover topics such as conductor ampacity, overcurrent protection, and wiring methods. Conductor ampacity refers to the maximum current that a conductor can safely carry without overheating. The NEC provides tables that specify the ampacity of different types of conductors based on their size, insulation type, and installation conditions. Overcurrent protection is provided by circuit breakers or fuses, which are designed to interrupt the flow of current in the event of an overload or short circuit. The NEC specifies the maximum size of overcurrent protection devices that can be used for different types of circuits. Wiring methods refer to the way in which conductors are installed and supported. The NEC recognizes a variety of wiring methods, including conduit to cable tray and open wiring. The choice of wiring method will depend on the specific application and the environmental conditions. In the scenario described, the use of 6 American wire gauge THHN conductors for the 220-volt circuit is likely appropriate, as THHN insulation is commonly used for general-purpose wiring in dry and damp locations. However, it is important to verify the ampacity of the conductors based on the specific insulation conditions and to ensure that the conductors are properly protected by an overcurrent protection device. The use of 18 American wire gauge THHN conductors for the control wiring is also likely acceptable, as long as the conductors are properly protected and are not subjected to excessive voltage drop. However, It is important to verify that the conductors are sized appropriately for the control circuit load and to ensure that they are not overloaded. In addition to the NEC, there may also be local codes and regulations that apply to the electrical installation. It is important to check with the local authorities to determine if there are any additional requirements that must be met. In conclusion, the mixing of control wiring and a 220-volt circuit in the same raceway without a suitable barrier is a code violation under NEC Section 300.3c. To comply with the code, a ground bar or other suitable barrier must be installed, or a multi-conductor cable must be used. In addition, the installation must comply with all applicable requirements for rooftop installations, including those related to wet locations, support and protection of wiring, and grounding. Always consult the NEC and other applicable codes and standards when designing and installing electrical systems, and seek the advice of a qualified electrician if you have any questions or concerns. The information provided is for general guidance only and should not be considered a substitute for professional engineering advice. It is essential to consult with a qualified electrical engineer or licensed electrician to ensure that any electrical installation meets all applicable codes and standards and is safe for its intended use. Let us look at why the National Electrical Code exists and what it seeks to achieve. The NEC is a comprehensive set of guidelines and regulations designed to ensure the safe installation and maintenance of electrical systems. It is developed and updated regularly by the National Fire Protection Association, or NFPA, and is widely adopted by jurisdictions throughout the United States. The NEC is not a law itself, but it is often adopted into law by state and local governments. This means that compliance with the NEC is legally required in many areas. The primary goal of the NEC is to protect people and property from electrical hazards. Electrical hazards can include electric shock, electrocution, fire, and explosions. The NEC addresses these hazards by establishing minimum safety standards for electrical installations. These standards cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is organized into chapters, articles, and sections. Each section of the NEC addresses a specific aspect of electrical safety. The NEC also includes tables and figures that provide detailed information on topics such as conductor ampacity, conduit fill, and grounding electrode sizing. The NEC is constantly evolving to keep pace with new technologies and changing safety concerns. The NFPA publishes a new edition of the NEC every 3 years. Each edition incorporates revisions and updates that reflect the latest knowledge and best practices in electrical safety. Compliance with the NEC is essential for ensuring the safety of electrical systems. Failure to comply with the NEC can result in serious consequences, including fines, legal liability, and personal injury. The NEC is a complex and comprehensive document. It is important for anyone involved in the design, installation, or maintenance of electrical systems to have a thorough understanding of the NEC requirements. There are many resources available to help people learn about the NEC, including training courses, seminars, and online resources. In addition to the NEC, there may also be other codes and standards that apply to electrical installations. These codes and standards may be developed by state or local governments, or by industry organizations. It is important to be aware of all applicable codes and standards and to ensure that electrical installations comply with all requirements. Electrical safety is a shared responsibility. Everyone involved in the design, installation, or maintenance of electrical systems has a role to play in ensuring that these systems are safe. By following the NEC and other applicable codes and standards, we can help to prevent electrical hazards and protect people and property from harm. Now let's talk about the specific sections of the NEC that relate to the scenario described in the initial question. As mentioned earlier, NEC Section 300.3c prohibits the mixing of conductors of different systems in the same raceway without a suitable barrier. This section is intended to prevent electrical hazards that can arise from the close proximity of high and low voltage conductors. In addition to Section 300.3c, there are several other sections of the NEC that may be relevant to the scenario. These sections include Section 310.15, which addresses conductor ampacity, Section 240.4, which addresses overcurrent protection, and Section 250.4, which addresses grounding. Section 310.15 specifies the ampacity of different types of conductors based on their size, insulation type, and installation conditions. The ampacity of a conductor is the maximum current that it can safely carry without overheating. It is important to select conductors with an ampacity that is sufficient for the load that they will be carrying. Section 240.4 specifies the requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. The NEC specifies the maximum size of overcurrent protection devices that can be used for different types of circuits. Section 250.4 specifies the requirements for grounding. Grounding is the process of connecting electrical equipment to the earth. Grounding helps to prevent electrical shock by providing a low impedance path for fault currents to flow back to the source. In addition to these specific sections of the NEC, there are also general requirements for the installation of electrical wiring. These requirements cover topics such as wiring methods, conductor identification, and box fill. Wiring methods refer to the way in which conductors are installed and supported. The NEC recognizes a variety of wiring methods, including conduit, cable tray, and open wiring. Conductor identification refers to the marking of conductors to indicate their purpose. The NEC requires that conductors be identified by color or other means. Box fill refers to the amount of space that is available inside an electrical box. The NEC specifies the maximum number of conductors that can be installed in a box of a given size. The NEC is a complex and comprehensive document. It is important for anyone involved in the design, installation, or maintenance of electrical systems to have a thorough understanding of the NEC requirements. There are many resources available to help people learn about the NEC, including training courses, seminars, and online resources. In addition to the NEC, there may also be other codes and standards that apply to electrical installations. These codes and standards may be developed by state or local governments or by industry organizations. It is important to be aware of all applicable codes and standards and to ensure that electrical installations comply with all requirements. Electrical safety is a shared responsibility. Everyone involved in the design, installation, or maintenance of electrical systems has a role to play in ensuring that these systems are safe. By following the NEC and other applicable codes and standards, we can help to prevent electrical hazards and protect people and property from harm. Now let's explore some practical considerations for addressing the code violation in the described scenario. If the existing installation violates NEC Section 300.3c by mixing control wiring and a 220-volt circuit in the same raceway without a suitable barrier, there are several possible corrective actions that can be taken. The best approach will depend on the specific circumstances of the installation, including the size and configuration of the raceway, the number of conductors involved, and the available space. Firstly, one option is to install a ground bar or other suitable barrier within the raceway to physically separate the two systems. This is often the most straightforward and cost-effective solution, especially if the raceway is large enough to accommodate the barrier without overcrowding the conductors. The ground bar should be securely mounted and properly grounded to ensure its effectiveness. Secondly, another option is to replace the existing wiring with a multi-conductor cable that is specifically rated for the voltage and current requirements of both the control wiring and the 220-volt circuit. This option may be more expensive than installing a barrier, but it can provide a cleaner and more organized installation. When selecting a multi-conductor cable, it is important to consider the ampacity of the conductors, the insulation voltage rating, and the environmental conditions in which the cable will be installed. Thirdly, a third option is to install separate raceways for the control wiring and the 220-volt circuit. This is the most labor-intensive and expensive option, but it provides the best level of separation between the two systems. If separate raceways are installed, it is important to ensure that they are properly supported and protected from physical damage. Fourthly, regardless of the corrective action that is taken, it is important to verify that the installation complies with all applicable requirements of the NEC and other codes and standards. This includes ensuring that the conductors are properly sized and protected, that the wiring methods are appropriate for the environment, and that the equipment is properly grounded. It is also important to document the corrective action that is taken and to keep a record of the inspection and testing results. In addition to the corrective actions described above, there are also some preventative measures that can be taken to avoid code violations in the first place. These measures include carefully planning the electrical installation before starting work, using properly rated materials and equipment, and following all applicable codes and standards. It is also important to provide adequate training for electricians and other personnel who are involved in the installation and maintenance of electrical systems. By taking these preventative measures, it is possible to reduce the risk of code violations and ensure the safety of electrical installations. Now let's discuss the importance of proper grounding in electrical systems, especially in relation to the scenario of mixed voltage wiring. Grounding is a critical aspect of electrical safety, and it plays a vital role in protecting people and equipment from electrical hazards. The purpose of grounding is to provide a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and interrupt the flow of current. This helps to prevent electrical shock and fire hazards. In the scenario of mixed voltage wiring, proper grounding is even more important, as it can help to mitigate the risks associated with insulation breakdown and accidental contact with live parts. When high and low voltage conductors are run in close proximity, there is an increased risk of insulation failure, which can lead to a short circuit between the conductors. If the system is properly grounded, the fault current will flow back to the source through the grounding path, causing the overcurrent protection device to trip and to energize the circuit. Without proper grounding, the fault current may not be sufficient to trip the overcurrent protection device, which can result in a sustained arc and a potential fire hazard. In addition to protecting against short circuits, grounding also helps to protect against electrical shock. If a person comes into contact with a live part of an electrical system, the current will flow through their body to ground. If the system is properly grounded, the grounding path will provide a lower impedance path than the person's body, causing most of the current to flow through the grounding path rather than through the person. This can significantly reduce the severity of the electrical shock. The NEC specifies detailed requirements for grounding electrical systems. These requirements cover topics such as the size and type of grounding conductors, the location of grounding electrodes, and the bonding of metal parts. It is important to follow these requirements carefully to ensure that the grounding system is effective. In the scenario of mixed voltage wiring, it is particularly important to ensure that the grounding system is properly designed and installed. The grounding conductor should be sized appropriately for the fault current that it may be required to carry, and the grounding electrode should be located in a manner that provides a low impedance path to ground. It is also important to bond all metal parts of the electrical system together to create a continuous grounding path. In addition to the NEC requirements, there may also be local codes and regulations that apply to grounding. It is important to check with the local authorities to determine if there are any additional requirements that must be met. Grounding is a critical aspect of electrical safety, and it should never be taken lightly. Proper grounding can help to prevent electrical shock, fire hazards, and other serious electrical problems. Now we will elaborate on the types of barriers that are considered suitable for separating different electrical systems within a raceway or enclosure as per the NEC requirements. As previously discussed, NEC Section 300.3c mandates the use of a suitable barrier when conductors of different systems are present in the same raceway, cable tray, or enclosure. The purpose of this barrier is to provide physical separation and electrical isolation between the systems, preventing potential hazards like insulation breakdown, electromagnetic interference, and accidental contact. Firstly, a ground bar is a common and effective type of barrier. A ground bar is a conductive metal bar that is connected to the grounding system of the electrical installation. It serves as a convenient point for terminating grounding conductors and bonding metal parts. When used as a barrier, the ground bar is typically installed within the raceway or enclosure, creating a physical separation between the different systems. The ground bar should be securely mounted and properly grounded to ensure its effectiveness in diverting fault currents. Secondly, insulated dividers are another type of suitable barrier. These dividers are made of non-conductive materials like plastic or fiberglass and are designed to physically separate conductors within a raceway or enclosure. Insulated dividers can be particularly useful when space is limited or when it is necessary to provide a high degree of electrical isolation. They are available in various shapes and sizes to accommodate different conductor configurations. Thirdly, separate compartments within the raceway or enclosure can also serve as suitable barriers. This approach involves dividing the raceway or enclosure into distinct sections, each dedicated to a specific electrical system. The compartment should be constructed of a rigid material that provides adequate physical separation and electrical insulation. This method is often used in larger enclosures where there is ample space to create separate compartments. Fourthly, metal barriers can be used if they are properly grounded. Similar to ground bars, metal barriers provide a physical separation between different electrical systems. However, to ensure safety, these barriers must be effectively grounded to prevent them from becoming energized in the event of a fault. The grounding connection should be robust and reliable. The selection of the appropriate barrier type depends on several factors, including the size and configuration of the raceway or enclosure, the voltage levels of the electrical systems, and the specific requirements of the installation. It is essential to consult the NEC and other applicable codes and standards to ensure that the chosen barrier meets all safety requirements. Regardless of the barrier type used, it is crucial to ensure that it is properly installed and maintained. The barrier should be securely mounted, free from damage, and regularly inspected to verify its effectiveness. Any signs of deterioration or damage should be promptly addressed to prevent potential electrical hazards. In addition to the physical barrier, it is also important to consider the labeling and identification of the different electrical systems within the raceway or enclosure. Clear and accurate labeling can help to prevent confusion and ensure that electricians and other personnel are aware of the presence of different voltage levels. The labeling should comply with the requirements of the NEC and other applicable codes and standards. Proper labeling can also help to facilitate troubleshooting and maintenance activities. In summary, a suitable barrier is essential for safely separating different electrical systems within a raceway or enclosure. Ground bars, insulated dividers, separate compartments, and properly grounded metal barriers are all acceptable options, provided that they meet the requirements of the NEC and other applicable codes and standards. The selection of the appropriate barrier type depends on the specific circumstances of the installation. Regular inspection and maintenance are crucial for ensuring the continued effectiveness of the barrier. In addition to the physical barrier, proper labeling and identification of the electrical systems are also important for safety and convenience. By following these guidelines, it is possible to minimize the risks associated with mixing different electrical systems and ensure a safe and reliable electrical installation.